So yes, last class what we saw is Lagrange-Euler formulation, correct? So today we'll commence with Newton-Euler formulation. Okay. Okay then. So this method is not very much different. This is a long way back. You've been doing this Newton formulation and Euler formulation in standard problems of engineering mechanics and others. Okay. So this is just an extension of that which is put in a new way so that you can do things which are related to multi-body dynamic system like robotics. Okay. So yes, let us start with this. So let us take just one link of a robot. Okay, just one link. What all forces that comes on it? Okay, let me just analyze that first. Okay, so yes, this is a link. It may have a link prior to this. It also has a link which is after this. Okay, so this link applies forces on the link which is prior to this, and it also sees a force and moment from a link which is after this. Okay, so these two are those forces. This is, okay, I'll just highlight them. Okay, so this is the force which is exerted by the link to the link which is before to this. Okay, and this is the corresponding moment for it. And similarly, this two are the forces and moments which is sees from the link which is connected after this. Okay, so that's these two are external forces that are acted on this link. Okay, and then this is its own angular velocity. Mind it, all the forces, moment, velocities, angular velocities are in three-dimensional space. Okay, so this is omega and this is linear velocity VCI. Okay, and both are observed over here, that is center of gravity of that. Okay, and mg is the force due to gravity that it sees. Okay, okay then, so mi is the mass of the link I. Okay, VCI is the linear velocity of the centroid of the link I with respect to OXYZ. What is OXYZ? That is the global frame about which all the link masses are represented, all the forces are represented. Okay, so this is the universal frame about which whole of the robot system is placed. Okay, now Fi minus 1 I and Fi I plus 1. So these are coupling forces applied to the link I by links I minus 1 and I plus 1. Okay, respectively. And then similarly, this is moment acted on this and moment acted by this to the links which are coupled to this. Okay, so this is the ith link, and then II is the centroidal inertia tensor. I is the moment of inertia tensor. Okay, about centroid. Omega I is the angular velocity vector. Okay, so this method, Newton-Euler formulation, basically will use all the forces. Basically, it draws the free body diagram of this link independently one by one, and then all the FBD equations are clubbed together, solved to get the external forces as well as internal forces. So all the forces are to be evaluated. In case of Lagrange-Euler, we were not bothered about any internal forces. That is something which makes it very easy, but that is also a shortcoming. If at all I want to know what is the interaction force between two links. Okay, so we never come to know what are the interaction forces between two links if we solve using Lagrange-Euler formulation. But in case of Newton-Euler, that force is also calculated and we get to know that as well. Okay, that helps me in doing some other analysis, if not just the equation of motion. Okay, some other analysis. Okay, then So now we'll see the free body diagram of individual link I. This is the link I about which I am talking about. So yes, so this is the force equation. What are the forces that acts on it? This one is Fi minus 1 I, that is this one. This is because of the link which is connected before this. Okay, and then again another force which is here, that is I plus 1. So I plus 1 link comes after this, I minus 1 link comes before to this. So this minus this is actually the resultant force that is acted on this link. Okay, and force due to its own weight. So that is there always. So resultant force creates the acceleration. So VCI dot, V is the velocity, VCI dot is the acceleration of this body. So mass into acceleration is that is equal to resultant forces that acts on this link. So that is straightforward, quite simple. So this is Newton equation. So what is the Euler equation? It is the rotational part which is similar to that. So now you will have Ni minus 1 I, that is the moment which is from here to this link, and then Ni plus 1. So Ni plus 1 is the moment that is transmitted from this link to the next link. So what it itself sees is a negative sign of that, is it not? So this is the resultant moment due to external forces. Okay, so now what are the moments which are coming here due to internal forces are, see, so you have two vectors, two are easily known if you know the geometry of the system. So and if you know, you can do the forward kinematics of this, so very well you know this vector, this vector. Let me wipe off a bit now so that things becomes very clear. Yes, okay. So yes, so this vector is very well known. You know the link length. If length, that is the distance between two zi axis, you already know the dh parameters. That means if you know the xi axis, x axis of the link itself, so that is basically directed over here, and distance between them is its magnitude. So this vector can now be represented as Ri minus 1 I, Ri minus 1 I. And now that you also know the position and orientation of this link, if you have done forward kinematics, so you basically know this vector very well. So if this is known, center of gravity location is also known. If a link geometry is known, you always know where is its center of gravity, right? So this is always known in its own frame, in its own frame. So this vector is also known. Okay, so you can easily calculate how much is this. So yes, so if this vector is known, okay, so that is basically Ri minus 1 I and RICI, this and this is known. So I have effectively calculated this vector. Okay, so this vector into the force vector, that is this vector, gives you the moment experienced at this location because of this force. Okay, so that is this. And then similarly, you know this, you have this force in hand. So because of this force, what is the moment that is acting here is effectively this much. Okay, so these two are the moments at the center of gravity location, okay, CG location, because of two external forces. So due to external forces, these are the moments, these are the external moments that are acting on it. So now this will create all sorts of motion. So let us see what motion is caused and what are the moments, forces which are related to that. Yes, so this will create I omega dat. I omega dat. The way you create force is equal to mass into acceleration in the top equation, first equation. Over here it is resultant moment will create I into omega dot. Moment of inertia into angular acceleration. So this is the first term, and the second term, that is not so easily visible, that is also there, that is because of gyroscopic torque, omega cross I omega I. Okay, so this is what is the gyroscopic torque, because the motion is not just in a plane, okay, it is in a three-dimensional space. So this force is also there. Okay, this torque, this moment is also visible. Okay, so yes, so finally you see all these. So this is what is the combined Euler equation, and this is the Newtonian equation. So these two equation makes it all. Okay, so for each and every link you can create these two pair of equations. Why equations? Because each of these is three sets of equation. Why? F is basically a vector, it contains fx, fy and fz. Similarly, moment nx, ny and z. Okay, so total 6 equations are formed for each link. Okay, okay, so now we'll move ahead now. Okay, the complete equation of motion of the robot is obtained by evaluating both the equations, both these equations for all the links, that is I is equal to 1 to n. So n into 6 equations. So this is 6 equation, n 6n equation you will see. Combining them all together, you can eliminate all the internal forces, and finally what you get is the forces that we need, that is the joint torques. Okay, that is the torque over here you can calculate. So how that is done? So yes, this is a method which works on forward recursion. Why? What is forward recursion? Forward recursion, why that is the term which is coined here? Let us just see. Okay, so now let us see what is forward recursion. Okay, so in case of torque you have seen, let us say it is a serial chain system obviously. So this is first link, you have yet another link, you have another link which is connected next to it. So yes, whatever is the velocity that you see here is resultant of motion which is at all the joints prior to this, is it not? So if this is moving, this is moving with some velocity. If this is moving, this is again moving with some other velocity in some other direction. Okay, obviously this cross, if this is rotating, this is rotating, and this is the distance, so this will be the velocity due to the second joint motion, this is the velocity due to the first joint motion. If this is moving, this is the distance, and you see again a velocity v3. So sum of all the velocities will be, sum of all these will be the resultant velocity due to motions of all the joints. Okay, so this is known as forward recursion. That means you have to iterate from this to this to this and finally to the end. Okay, forward way you have to move. Okay, so velocity is because of all the links which are before to this. Okay, so this is forward recursion I am talking about. So yes, joint velocity and accelerations are calculated in forward recursion. That means you have to move from bottom to the top. Okay, then joint torques and forces are evaluated in backward recursion. Now what is backward recursion? Let me just go there. Okay, that you have seen earlier also when we were doing statics. Okay, so again let me draw this first link, second link, third link at least. Okay, so torque acting over here is because of motion of this, is it not? Torque acting over here is because of motion of this. Okay, so that is causing some torque. Again over here when you see, it is because of motion of this as well as this. So combined motions will create a torque which is here. Okay, If this is tau 3, this is tau 2, this is tau 1. Those are the torques. So what is the torque which is here? It is due to combined motion of this as well as this. So that is a backward recursion. That is a backward recursion. Things are not that trivial as it appears. Okay, definitely in case of 3 dimension, it is not just the torque, it is moment that comes, and finally we resolve them along the axis to get the torque. Okay, because it is planar, it is so trivial. Okay, so that is what is backward recursion. So joint torques and forces. In case of prismatic joint, it is force. Forces are evaluated in the backward recursion. So using these 6 equations for each link into n number of equation, n is the degree of freedom of that robot, you do forward recursion first, you obtain all the velocities and acceleration. So that goes here, velocities and all the accelerations. Okay, so that goes here, this is the acceleration. First you calculate the velocity, then you calculate the acceleration. Okay, and you substitute it here. So using forward recursion, using forward kinematics, taking derivative of that, you calculate the velocity and that you substitute here. Now this equation is complete. Now you do backward recursion. So because you know, you start attacking with the last link first. Okay, this has got least number of variables. So you do backward recursion. Now that you know the velocity of this, you can velocity and acceleration of this, you calculate the torque. Now that you know this, you have to come back because you know this, you know the forces which are here. Okay, forces and moment that is coming due to this motion. Okay, so you know this, you can start evaluating this one for this one, and then once you done this, you calculate this force and moment, you come back and finally get this value. Okay, so that is how you do backward iteration. We'll do it and we'll see how it is working. Okay, note that joint torque is not explicitly involved in the Newton-Euler formulation. In case of Newton-Euler, torque is not present, it is moment which are there. Okay, you have to resolve that component along the axis of motion and get the torques. Okay, correct? So that is what. So this is just a philosophy of what is done in case of Newton-Euler formulation. So what explicitly you do is free body diagram of individual links, get the 6 equations. Okay, 6 means compact 3 and 3 equations. Altogether equation number 1 is 3 equation and another Newton and Euler equations, 2 equations, compact equation. Do forward iteration, get these, do backward iteration and calculate the joint torques and forces. So mostly you have all the numerical values, you don't normally do the way it looks like in general equation. Okay, and things becomes very simpler. Okay, so let us do one example. Let us start with a 2R manipulator using Newton-Euler approach. Okay, over here what is given is, it is a planar uh, age old link now for us, because we have been dealing with this system for kinematics, for Jacobian, right, for velocity calculation and many more. Okay, so now you know, you are familiar with this type of system. Okay, so now you see what I have done. So this is your L1 link length, L2 is the link length 2, LC1 is the position of center of gravity of first link. This is LC2, that is position of LC2, that is center of gravity with respect to this point, because you know this link as a whole. Okay, so these two locations are given. Okay, what are unknown is F12. What is F12? It is force that is acted by, or it is getting this force by this link. Okay, that is the interaction force between these two links. Okay, F12, that is interface between 1 and 2. Again you will have a force which is here, that is between the ground frame and the first link, F01, F12. There is no link which comes after this, so there won't be any interaction force after this. So that becomes makes things very, very simpler. What is theta 2? That is the joint angle. Tau 2 is the value that we want to obtain. Tau 1 is again that is we want to obtain. These two are joint torques that we will be calculating. Okay, moment of inertia, if the link geometry is known, mass distribution is known, moment of inertia tensor is known. Mi is the mass of that link. Similarly for link 2. So these are the variables that are known. We can calculate this velocity. Is it not? If we can do forward kinematics, we can take derivative, we can definitely calculate this velocity. So let us do it. Okay. So this is your Newton-Euler equation. This is the first equation, that is the Newton equation. Okay. That is the force balance equation. That is force 0 to 1. Okay. That is the ground to first interaction force. Next comes first to second, this is another interaction force. This is the resultant force. This effectively is similar to what we did over here. Okay, exactly this equation is put over here. Okay, so just the variable number is there now. Okay, it is not in a generalized I plus 1 case. I am dealing with link 1. Okay, so if you take this, it becomes F01 over here, F01, F12, M1Z, M1 VCI. Okay, so this is quite trivial. Similarly, we will do for the rest of the thing. Okay, so this is the first equation, M1G and M1 VC, center of gravity velocity. Okay, if this moves with certain velocity, it is this velocity. Okay, velocity and dot of that, that is the acceleration of that. Okay, so that is the center of gravity, acceleration of center of gravity of first link. So that is what is the free body diagram and first equation of motion. Okay, that is the force balance equation. Now next, similarly you can draw the moment equation. So n01 here and 1 2 that comes here. Okay, so that is the resultant moment, external moments that acts on this, and then R1C1 F12 that is the force, if this is the force, R1C1 is this distance 1 to this distance. Okay, this is 0, mind it, so 1 is this, so that is the force. R0C1, this is this distance, and F01, that is this force. Okay, so these two are, because of these forces, moment that is created at center of gravity location. This is this term, and effectively there won't be any Coriolis term over here because this is just one link. So just one term is there, that is moment of inertia into angular acceleration. So that is there. Okay, so that is there. It is equal to 0. Okay. Now these two equations will be, inertia over here is its scalar inertia, because this is just one link, it is scalar inertia, otherwise it will be a tensor. Okay, so centroid of each link is assumed at its center. It is just an assumption, it may not be there. Even if you don't assume, this is a general equation, so RC1 and RC, these two distances may not be equal. If it is at center, it is equal, otherwise it is not. This is in a general form. Okay, now similarly for link 2, for second link, F12 is there, only this force is there, there is no force from the link which is next to it, because there is no link at all. Okay, so there is another force, this is the force due to gravity and force due to acceleration, Vc2 and m2. So effectively this is the force. Okay, and then similarly for moment, again there is no external moment from this side, only this moment will exist. Okay, and then this force will create a moment over here, so that is this one, and this is again scalar moment of inertia into angular acceleration. So this is also a simpler one. Now how to attack this? This is first pair, another pair is here. This is for link system 1, this is for link system 2. Okay. Mind it, this is so far so clear, should not be any difficulty. This is just Newton-Euler equation. Okay. For planar system, for planar manipulator like this, moment is equal to torque because it is exactly at this axis. It is not a three-dimensional vector. So I can simply write Ni minus 1I as 0, 0, tau 1. It is now in terms of a vector. Okay, tau 1, torque is equal to moment, but it can be expressed as 0 moment along x, 0 moment along y. Only there is just one moment that is perpendicular to this plane, that is the torque that is acting over here, tau 1, this is tau 2. Okay, so that is what for 1 and 2 links. For planar system it is quite trivial, for others it may not be this simple. Okay, so yes, so now I'll try to eliminate different variables. I don't want these terms to be there. Okay, this is something which we don't want, so I'll simply eliminate this. I start working from this, I substitute it to the this one. Okay, to this one. Okay, ultimately what I get is, eliminating f12, we get tau 2 is equal to, that is in the second equation I have substituted that, so I got this. Similarly f01, if you eliminate, you get this. So it is just two variables and two equation you have to eliminate. Okay, it is quite trivial, so just it is just those substitution. You can work it out yourself also. I'll share this slide. Okay, so that is what I have done. So these are the two torques that we need. Okay, now solving these two, I have first, using four equations, two substitutions are made, internal forces are eliminated. Now I am again left off with two variables, that is tau 1 and tau 2. These two further can be solved and can be eliminated. Now first what I have to do, I have to find out this, that is the acceleration, that can be done using forward kinematics. You know that very well. So what is the location of center of gravity? If this is the link, I will do it for you, first link at least. This is your x, this is your y. So if this is LC1, center of gravity, LC1 distance from this, okay, this is your theta 1. So this is LC1 cos theta 1 and this is LC1 cos theta, sin theta 1, sorry, this is sin theta 1. Quite trivial. So yes, so this is the center of gravity location. Similarly, if you have another link which is coming next, so if this is the center of gravity location, so what is this? This is the distance, this is L2 or simply LC2, LC2, LC2 distance, this is already given, and whole of this distance is L1. So this is already known, L1. So if you do in a similar manner, you already know theta 1 and theta 2 angles, you can obtain C2 location as this one. So this is your x, this is your y for this location. Okay, so now you know the center of gravity location C1 and C2 in terms of vectors. These two vectors are known, C1 vector and C2 vector. So these two vectors are known. Okay, so now you know what I am going to do next is this. I will just take derivative of these two. If you take derivative of these two, what do you get? You get velocities. If that is the position, derivative of position is velocity. Okay, so this will also involve, if you take derivative of just this one, so you see it, what do you get? This is a constant, so cos, derivative of cosine is sin A, theta 1, and then theta 1 itself is a variable. So you will get theta 1 dot. So what is that? This is angular velocity of first joint. Similarly, you did this, you got this, and taking derivative of this, you can quickly obtain this. So these two are the velocities. Okay. Again, you take derivative and you can obtain this as well. Okay, you can obtain Vc2 dot. Okay, and similarly, omega, if it is omega is theta dot, so omega dot is theta double dot. Okay, so again take derivative of this and you can obtain Vc1 dot or Vc2 dot. So those are the things which are required here. Okay, so that using this forward kinematics equation, you can evolve with that, because you know the joint angle at any instant of time. Okay, so you can calculate these and you substitute them using, this is what is the forward iteration. Okay, this is what is the forward iteration. You go from bottom to top, you put them all here. Okay, so you have everything in place now. You have this, you have this, you know this, you know this, each and everything's are known. So these two equations is now sufficient to get the torques, which is unknown, tau 1 and tau 2. Got it? So you can quickly write this equation in this form. Okay, so after solving, you can rearrange that the way we did it in Lagrange-Euler formulation. You can write this in this form. Okay, so what are these terms first? So what this term says, what is this term? What is this term? Overall, this is an inertia matrix. This is a generalized inertia gym. Okay, inertia matrix is multiplied with acceleration matrix. So first term of inertia matrix is a combination of something. What does it say? It has its own meaning, you know. What is it actually? I'll tell you. Okay, so let us draw this two link once again. Okay, this is very interesting, you see. So this is your first link, this is your second link. So at any instant of time, this is theta 1, this is theta 2, and effectively this was theta 1 also. Okay, so this is your second mass. So moment of inertia, I11 term, you see, it is effectively combined moment of inertia of this system, assuming joint 2 is totally immobilized. That means you have frozen this in this orientation. So this link shape of this system is something like this. Okay, so now your link is not the way it was earlier. You can draw your links, which is permanent link of this shape. This is theta 1 and this is theta 2, and this is frozen. Okay, and this link is of this shape, and now this is the moment of inertia of a shape, of a link which is shaped like this. Okay, so this is what is the physical meaning of this term I11. That means it says your link is of this shape and this is nothing but moment of inertia of this system. Okay, that is first term. Now the second term, I12 or 21, I12 or 21. Okay, that is the diagonal terms. Okay, that is interaction between the joint. Okay, if you remember your moment of inertia, this was Ixx, this is Ixy, coupled moment of inertias, no, Iyx and Iyy. So these two terms are principal moment of inertia, where these two are product moment of inertia. Physically, it means it basically interprets the interaction between the two links. Okay, effect of moving one link on the other one. Okay, so it basically represents that. Okay, so that is the interaction between the two links. So these two terms are same. Okay, and the last term, what is this? Moment of inertia of link 2 about joint 2? It is quite simple. So, it is purely the moment of inertia of second link of this is, if this is second link about joint 2. Okay. So, that is what it is. Okay. So, M2 LC2 square plus I2. I2 is nothing but moment of inertia about its center of mass. I2 is moment of inertia about its center of mass. So, what is the moment of inertia about this? About joint 2. This is joint 2. So, if this is the distance LC2, so if this is the mass, it has mass of M2. So, overall it will be M2 LC2 square. This is using moment of, this is parallel axis theorem. So, that is what it is. So, moment of inertia of second link with respect to joint 2. So, it is that. Okay. So, 4 terms are there. This one is coupled moments, moment of inertia, that is interaction between these two joints. First one was a link which is of this shape. If it is moving, what would be moment of inertia about this point? So, it expresses this, whereas this is the term which expresses moment of inertia about this for second link. Okay, got it? So, that is what is the physical meaning of this. Rest all terms are not that trivial though. So, that is effectively expressing the centripetal terms. As I have expressed earlier also, explained earlier also, this basically, that second term of this is the torque which is happening due to the centripetal forces, okay, and this is because of Coriolis forces. You see, it has product of angular velocities, and then finally this is the gravity term, torque due to the effect of gravity. Okay, so this term is, it looks like this. If you derive it, finally Coriolis, it looks like this, and the gravity term is like this. So you see, there is no velocity term which is associated here. That means this torque is always there if gravitational force is present, G is there. If it is in space, this term will be equal to 0. If the robot is not moving, this term will always be there, irrespective of if it is in, if it is on earth, it has to be there. If it is on Mars, again it will be there. It only depends on G. It doesn't depend on velocity or acceleration. Got it? So that is what is this. It doesn't depend on this. Whereas these terms is only present when you have some motion, velocity or velocity dot. Okay. So it doesn't depend. So it will be always present if the robot is moving, even if it is in space. Got it? So interpretation is quite similar to that. Effectively, you got same equation as you obtained in case of Lagrange-Euler formulation earlier. Okay, so there is no difference, method is different. Yes, in between what you got some additional information in case of Newton-Euler system is you got these forces, interaction forces, that may help you to understand the stresses which may be there at the joint. Okay, that Lagrange-Euler never allowed you to do this. Yes, you have more number equations that are to be solved, but yes, it is not that programming friendly, but yes, this also can be programmed iteratively some. Okay, so yes, I would suggest you go through this book which I have mentioned here. Okay, with that you can get a similar uh, explanation. Okay, I hope this I have already explained the interpretation of this. So yes, varying moment of inertia, this varies, moment of inertia varies, inertia matrix varies because this joint angles are changing. So every time you see this link lengths, distances of different center of mass, it is changing. So system inertia matrix I11, I12, I21, I22. So this is the inertia matrix. This keeps on changing. You see, it has terms which involves cosine of angle. Okay, cosine of angle. So those or the distance, if angles are involved, so that is changing, so these terms are variable as the robot moves. Okay, centrifugal force at this, let us say if it is this center of gravity, it will have a centrifugal force like this. This will create a moment over here, and finally the torque which is realized over here, is it not? So that is due to the centripetal. Again, because of combined motion of first link and the second link, okay, you will see a Coriolis component of force. So that is also visible in case of this. So this is the similar interpretation of all the terms of this. Again, the last term which was there, it is because of static, that is the gravitational force only. Okay, that's all. I think with this you get the philosophy how Newton-Euler system works for in order to solve the dynamics. Okay, but yes, this is not just complete. You need to do practice, practice and practice till you get to the things. Okay, you may have to take one numerical example, take some value and do it on some suitable software like MATLAB or Python, whatever you feel like. Okay, that's all.